Okay, we're going to look at the next day for probability 3.3, and I think it's 3.4. First, we're starting with understanding probability, a little more of what you did on Friday, and it should feel pretty comfortable. You've already told me what the probability of an event is. It's how likely that event will happen. Favorable outcomes over all possible outcomes was your definition on Friday. So, please take down this question and we'll answer it together. So if Mia has a 1 in 20 chance of making the all-star team, can you write that as a fraction? Alana, what is that as a fraction? Good. 1 over 20. And this is a fraction that we're really used to working with this year because you've seen a lot of these types in your Mad Minutes in our computational practice. So 1 out of 20 is what as a decimal, Dylan?
As a decimal, it's
0.05, good. And then we all know how to take a decimal and change it to a percent. We're adding a percent sign, so we add two place values, right? And this as a percent is 5%. So how likely is it that she'll make the all-star team? 5%. Okay, so usually in some of our everyday applications of probability, we see percents all the time. Like, have you ever heard a weather person say there's a 1 in 20 chance of rain? You have? It's not as often as hearing what? 5% chance of rain, right? I mean, we hear percents, but they could be giving us that fraction, 1 in 20. Most people like to hear it in a percent. I guess that's what we're used to hearing. Okay, complementary events. What operation do you think goes along with this idea of complementary? I think multiplication? Or what? I heard something else. I heard addition, so yeah, addition. So two events are complementary if only one or the other must occur. And it ends up being an addition of events, or of probabilities, I guess, really. So what is the probability of, let me have you take this first. The sum of complementary events always is 1. It always equals 1. So the probability, when we flip a coin, the probability of getting heads is what, Max? Flipping a coin. What's the probability of a head? 1 out of 2. And what's the probability of flipping tails? Right. And what is 1/2 plus 1/2? It equals 1. Okay, so we would say that heads and tails are complementary events. You're basically going to get one or the other when you flip a coin, is what that's saying. So if the probability of a team winning a game is 3 to 5, what is the probability that the team will not win the game? And you already used this, haven't you? So if their winning probability is 3 to 5, what is the not winning, Rachel? Good, 2 out of 5, right? Okay, so if we take that probability and add it to the winning probability, how do we add fractions? Someone give us the reminder. What do we add, Hannah? We add just the numerators. So 3 plus 2 is? And 5 over 5 is 1. So you can see that your chance of winning or losing this game would be 1. Now, what kind of a game do you guys many of you play where there's actually another outcome possible? Soccer. That's why I hate soccer. Actually, I like the game. It's fun, but I don't like ties. Don't you like to have, who here does not like ties? Now, who here does like ties? Don't be afraid, don't be shy. Okay, most of the class doesn't like ties. I think you like ties when your team is the underdog, right? And you would do, I mean, it would be such a long shot to win but you tied. You know what I mean? That was like a victory itself that you tied. So sometimes that's true. Not for the team who was supposed to win. I mean, it's kind of like a loss, right? Lauren? Okay, the second section, 3.4 today, you're going to look at disjoint and independent events. Something sounds different here. When we're looking at disjoint or independent events, these are compound events often that we're looking at here. And that word came up, I think, on Friday. Compound means what? More than one event, okay? They could take place at the same time or one after the other. Does anyone know a synonym for one after the other? One word that means, say it, Wesley. Good, consecutive. That's right. Consecutive events, one after the other. And at the same time would be simultaneous. Very good. We have 3 types of compound events that we're going to look at right now. The first is disjoint. Now, does that sound smooth to you? Disjoint? Disjoint? Like imagine you have joints. Would you want your joint to be disjointed? It doesn't sound good to be dissing it, right? Dissing your joint. These are events that have no outcomes in common. No outcomes in common. So, as an example, what is the probability on a die that you could roll an even or roll a 3? Are those 2 outcomes common outcomes? Can you roll a 3 that is even? An even 3? No, these are totally different kinds of outcomes, right? So the probability of rolling an even or a 3. I bet you could come up with this in your mind though. I mean, how many outcomes favor an even? Emily, on a regular die, 6-sided die, how many outcomes are an even? 3. And then how many outcomes are a 3? 1. And so what would you do to find the probability of rolling an even or a 3? What do you think? How many are in favor, how many outcomes in all are in favor of an even or a 3? So you're using what operation there? You're adding them, right? 3 are in favor of an even, and 1 is in favor of the 3. So when you add those up, 4 out of 6 are in favor of one of these outcomes, right? And can you reduce 4 out of 6? Can you reduce it? Come on. 4 out of 6, 2/3. You know that. Okay. You know, it's the, okay, another kind of compound event is known as independent events. I mean, independent events, we've already covered a couple. What do you think it might be? Like having a...
1.
Let's say you roll a die and...
Get 1. Exactly 1.
No. These are events, multiple events. So rolling a die is one event and flipping a coin. Okay? So the result of rolling a die doesn't affect the result of flipping the coin. They each have their own probability, right? The result of one does not affect the other. In the last example, if I roll an even, it affects the other, doesn't it? If I roll an even, I can't roll the 3. They're disjointed. But in this case, independent events, one doesn't affect the other. So if I roll a die, it doesn't affect what I get with a coin. They're just independent. So what would the probability be of rolling an even and getting a tails if I was to roll a die and flip a coin? Well, what is a method that you learned on Friday that you could use to like show all the possibilities? Yes.
And you can make a
Tree diagram, right? So what would you want to have in the upper part of the tree if you were going to do that?
the tails.
Heads and tails. So you could have I'm flipping a coin and I could get heads or tails, right? These are all the possible outcomes. And then what are the possible outcomes for the die?
Heads, 1, tails, 2, 3,
Good. So we have all of these, and then we have the same here. Now, tree diagrams are useful. You can kind of really see. I could get a heads with 1, all the way to a heads with 6. So there's 6 outcomes there. I could get tails with 1, all the way to tails with 6. So there's 6 outcomes there. So in all, how many total outcomes are there? And tails 2, tails 3, tails 4, tails 5. So there's 12 possible outcomes, but how many of them are even and tails? Well, here's tails over here. We got to go here. And even, T2, T4, T6. How many are there? 3 out of how many in all? 3 out of how many in all? 12. So would you want to make a tree diagram every time you're asked this type of question? You could, but you probably don't want to. It takes time. 3 out of 12 is the right answer, which is 1/4. But what is the math? How can we go from these values? We have 3 out of 6 are even on a die, and 1 out of 2 are tails on a coin. So what do we do with these fractions to get to 3/12 or 1/4? Chris? You can see it right here. That's right. You are multiplying, aren't you? You're multiplying the probabilities. 3/6 times 1/2 is 3/12, which gives us the probability of 1 out of 4. Okay? 3 out of 12 is 1 out of 4. So you are always welcome to do a tree diagram, but do you see the math behind it? You can just multiply your probabilities when you have independent events, and you'll have the probability for that compound event. Okay? Okay, and finally, dependent events, the last topic for compound events. Well, the word dependent means something is affecting something else, right? Dependent. Result of one affects the result of the. Okay, so the question here is, what would the probability be of randomly removing one color then removing another? Let's say you have these. Red, yellow, blue, green, and orange. Kind of interesting, but I have the colors that are mentioned here. Red, blue, green, orange, yellow from our blocks, our pattern blocks. So how many in all do I have? How many colors? 5 colors, okay. So what is the probability of me just pulling out a red randomly the first time? 1 out of 5, right? So if I reach in and pull out a color, I pulled out blue. So now if I keep it out, what probability remains that I will pull out a red? 1 in 4. Do you see how it changed? So this second selection, the second event of me pulling out a color, depends on what I did in the first event. That's why they're called dependent events. What happens the second time is dependent on what happened the first time. So the first time it was 1 in 5, the second it's now 1 in 4, and so if I pull out, I got the red, what probability remains? 0 out of 3, 0 probability now because I took the red out, it's gone, okay? So what does that look like? Something like this. The probability of a red at first would just be the probability of the red out of all 5, and then the second time I draw a color out, it depends on what happened in the first event. Let's see. I can't get back to my thing. Okay, so these are the 3 pages I would like you to complete.